Hello, everyone. I want to welcome you to this, our second Triumphs webinar, where we feature one of our primary source projects. My name is Danny Otero, and I'm the author of the particular project that we're going to talk about this hour. But before I do that, I should say a few words about what Triumphs is for those of you who are uninitiated here. As you see, this is a 5-year grant project that has assembled 7 people at 7 distinct universities across the country to design, to author, to revise, to classroom test, to evaluate, and ultimately to disseminate these primary source projects. These are classroom modules for teaching topics across the undergraduate mathematics curriculum. And their most important feature is that they do so through the engagement of students with primary historical sources. And this is a list of the some of the courses that can accommodate the projects that we currently have available. At the bottom of the screen is the Triumphs website, and if you visit that website, you can get your hands on any one of these projects. They are freely available, and in many cases, the author of the project can even send you a LaTeX source so that you can modify these as you see fit for your own classroom. In any case, the important thing to keep in mind about teaching with a PSP is this. It's more than just how you teach the content. It's about how you address the material as well. So Triumphs projects are designed with active teaching principles. So the expectation is that most of the time in the classroom, students will work in groups to make sense of the source text, usually through commentary that the author has written to surround the text and try to explain what's found therein. And the students engage the text through these tasks that are carefully crafted to help the students pull meaning out of the text. As you see in the paragraph at the bottom of the screen, this differs considerably from standard expositions, the way they generally learn through textbooks, precisely because we try to put the students in front of people who are no longer alive and have been dead for centuries, typically. And we feel that this gives the student a real sort of direct contact with the underlying mathematical ideas, because they're sharing in the writings of people for whom these ideas were much rawer than they are today. These presentations are engaging because they're rich with history. They tend to be a lot more concrete than what we see in standard textbooks. They're a lot less loaded with the jargon that we've developed to talk about these things, and the various subtleties are generally put to the side. And it can be a very eye-opening and sort of aha situation for many students. Let me move right now to a brief summary of what this particular project is. It's called A Genetic Context for Understanding the Trigonometric Functions. And the full project walks the students through these 6 vignettes in the history of trigonometry. By no means is this a comprehensive history of the subject. These are just episodes along the way. These were selected for or to satisfy a number of criteria, the most important of which was to see this long development of the subject over many, many centuries, and jumping from culture to culture even. So it begins with a description of Babylonian sexagesimal numeration, the link there being the modern way that we measure arcs and angles. I then bring the students to a reconstruction of Hipparchus' table of chords. He was known to have produced such a chord table, but records of this are lost, and Glenn Van Brumlin has attempted a reconstruction of the text, and that's what this table of chords is. Immediately thereafter, students read from Ptolemy's Almagest, a short application of this idea of using chord tables to work on an astronomical problem, in this case associating the angle of inclination of the sun to the length of the shadow it casts when a pole is driven into the ground. Then we jump to the to ancient Hindu sources. Here, Varahamihira is writing a portion of the Pankasiddhantika, and in Sanskrit verse, we find an encoding of a table of signs. This is a fascinating little vignette, because we see, first of all, the introduction of the sign, the modern sign, but also how the cultural requirements of putting this information into an oral form that was easy to transmit from adept to adept down the centuries gives us this verse form for the table. The fifth of the vignettes is Al-Biruni. This is the 11th century. We're now in Baghdad. And Al-Biruni is writing a work called The Exhaustive Treatise on Shadows. Again, we're looking at shadow casting clocks, so to speak. And here, Biruni is actually interested in what becomes the tangent, the cotangent, the secant, the cosecant. And those trigonometric forms appear in this work. Finally, we come to sort of the dawn of Western science. Regiomontanus, who wrote in the 1500s, gives the first mathematical treatment of trigonometry. We see a problem or two there. Let me walk you through examples from each of the 6 vignettes briefly. So the Babylonian numeration section is probably the shortest. I don't dwell on this much. I'm simply trying to explain what sexagesimal numeration is to the students. And so here's a brief bit of commentary, and the first task in the project is for them to come to terms with sexagesimal numeration. Here is the reconstructed table, you see that it's simply a two-column table where we have sexagesimal measures of both lengths of arcs and lengths of the corresponding chords across the circle. Both of these are in the same units of length. So where arcs are measured in arc minutes, so for instance, the first entry there, 7,30, that's 7/60 of minutes, and therefore 7 degrees, followed by 30 minutes. And so this first arc is 7.5 degrees. And the subsequent arcs down the column are simply multiples of this first 7.5 degree value. So you have 24 values here in multiples of 7.5 degrees. And alongside them are the corresponding chord lengths measured in the same units. You can tell this a number of ways. Perhaps the easiest is that the chord associated with that first arc is very close in value because it's a tiny angle, so the chord is nearly the same. You can infer from the last of the values in the table the chord corresponding to an arc of 180 degrees, what the diameter of the circle is meant to be measured by. In any case, let's move on. Here is a snapshot of the section on Ptolemy. What you see is a diagram, which is a schematic of the celestial sphere. The horizontal diameter there is meant to be the observer's horizon. The point on the circle labeled North Pole is, in fact, the North Star in the sky. The segment EG is a vertical pole that's been stuck into the ground. And the points on the circle at the positions, let's see, L, B, and H, these are positions of the sun at various times of the year. It's at B at the solstice, at the equinoxes. It's at H at the summer solstice. It's at L at the winter solstice. And at these different times of year, it casts shadows on the ground along segment GN. And the different shadows are related to the angles of inclination of the sun. And you see some of this text at the bottom of the screen that describes what's going on. So this is the first application that the students see of both arc length and chord distances. Let's see. I don't know if you folks can see this, but the panels of your faces are in front of my screen, so I'm moving them around. This is from Varahamihira. This is a portion of the verse where he encodes the sine table. The signs in Aries are in fact the signs of angles up to 30 degrees, because the first 30 degrees of the ecliptic circle are in the sign of Aries, the ram. And Taurus is the next zodiacal sign, so Taurus is code for angle measures between 30 and 60 degrees. And the numbers you see in the verse here are in fact the values of the signs of the angles that are spanned within this range of 0 to 30 and 30 to 60. Here, I need to figure out how to go. All right, let's put this aside. Here's from Al-Biruni. We have a similar picture to the one we saw in Ptolemy. shadow caster, the sun casts an angle. Biruni in the text is discussing the direct shadow of the sun, as well as the hypotenuse of the shadow. In the diagram, GE is your direct shadow, and BE is the hypotenuse of the shadow. Because the height of the pole, BG, is the unit of length, the length of the shadow and the length of the hypotenuse of the shadow are essentially stand-ins for the cotangent and the cosecant of the angle of inclination at E. So this is perhaps the first place where those two quantities were studied mathematically. Later in that same text, he creates a table of values for the various angles of arcs. For the cotangent, the arcs go from 1 degree down to 15. I only gave a portion of the table here. Of course, the cotangents of these angles are also the tangents of the complementary angles. That's what's tabulated in the second column. And the measures of these values are in the final column. You can see for angles close to 0, the cotangent is very large, in the same way that for angles close to 90, the tangent is very large. I have the students compare Biruni's values in his table with the values they can get from their calculator. And finally, there's the section from Regiomontanus. Regiomontanus is actually working with triangles that apparently have no connection with an astronomical problem. This is a purely mathematical situation. You've got some right triangle with certain dimensions, and you're trying to work out the measures of the unknown dimensions. So here, for instance, we've got the angle at B is 36 degrees, and the hypotenuse of the right triangle is given as 20 feet. Work out the lengths of the other two sides by using sine tables. And an invisible sine table is being used in this solution that Regiomontanus gives. Okay, so that's a quick run through of the project itself. I wanted to say a few things about it. There are source texts for all of the sections except for the first. I intentionally didn't want to get bogged down in a discussion of Babylonian numeration, so I didn't supply a source text there. I really just want to get them to understand where angle measure comes from, and that there's a history to it as well, and that it's very old. In the second vignette, Hipparchus table, this isn't really a source text, but for all practical purposes, the students believe it is, because they don't know the difference. And it has the same features for them as a primary source text would have. It's important in this project that connections be made with astronomy, because that's really where the genesis of trigonometry comes from. And this requires teaching the students some basic astronomy. They know very little about astronomy. In fact, 21st century students barely know what's in the sky anymore, because it's always so highly lit at night. They can hardly see anything in the sky at night. So they don't know these things, and it's news to them, for instance, that the sun moves across the background stars. And it's really an important feature because these were the problems that caused these ancient scholars to develop the ideas that now are trigonometry. I want to emphasize that this project does not substitute for a trigonometry course. It does not address all the standard topics and isn't meant to. It is designed instead to provide a context for the study of trigonometry to sort of address the question, why are we studying this? And to give a context for where the ideas come from. I'm convinced that if students have a sense of this, learning the standard topics, even in the traditional way, makes a little more sense. They can, it sticks to something in their brain that they wouldn't have had otherwise. The project does give a rationale for all of the 6 trigonometric values and discusses their interrelationships. There are important things that it doesn't do. For instance, you won't see the graph of a sine function or the graph of a tangent function because these are extremely late in the development of the subject. But the project is not meant to substitute for an entire course in trigonometry. So I try to get upfront about that. It does identify the standard Pythagorean relationships amongst the trig values, and it even looks at a type of half-angle formula along the way. So it's not devoid of content either. Let's talk about some of the important things about teaching with the project. It's really important that the students read ahead. Because engaging with a primary source text really means the necessity of having to do some very close reading. Many of our students have trouble reading at all, much less close reading. And anything that can be done to entice the students to engage with the text for the time you have them to do so is really important. Classroom time is meant to be used by the students to work on tasks, whether they do so alone or in small groups. That tends to be the best way I know. Once they've worked for a while in small groups, you can then get the students to talk amongst each other in the small groups, and ultimately from small group to small group across the classroom with you as moderator is perhaps the best way to get these ideas working in their heads. And then for homework, they should be asked to write up formal solutions to some of the tasks. The project has been implemented a number of times in the last 4 semesters in different ways. The full project can take up to 4 weeks to complete, depending on how quickly or slowly you move through it. The first implementation that I did in my classroom 2 years ago was not a full implementation. It was a quick implementation in 2 weeks where I didn't have the students work on all the tasks. The notes to instructors for this project give a list of tasks that I used in my 2-week implementation. So you can take a look at that in a copy of the project. Another implementer, Emily Casey at Pellissippi State. Emily, are you with us here? Well, Emily has implemented the project more times than anyone else I know. And in recent semesters, what she's done is explode the PSP. In other words, She uses the 6 vignettes across her trigonometry course semester and does a different vignette every 2 weeks or so across the semester. She really enjoys that way of working through it. I know of other people who have implemented portions of the text simply by extracting one or more of the vignettes from it. Let's see. Finally, what could go wrong? Well, a lot can go wrong. It turns out that students who already know some trigonometry may find this irrelevant to their interests and will could fight you as you try to ask them to look at its history. Another problem is when students aren't used to this kind of work. And so you ask them to work on a task and they sort of sit mutely in their small group or avoid trying anything at all and waiting for somebody else to give the answer. This requires you to really work on them, to give it a try. Once they've been successful at 1 or 2 tasks, it's a lot easier to have them work in this way. The project asked them to use some geometry of circles, and a lot of these students don't have much experience with geometry, so it can be a real struggle for them. Small groups are usually a good idea if one or another student has more geometric experience than another, then it can be used to the advantage. I've had one criticism leveled at the project that too many of the tasks focus on computation. I think that's a fair criticism. I just share that with you so that you know what I know about it. On the other hand, I have found a lot of the students who will take a course in which this is a natural resource, like a first-year trigonometry course. These tend to be students who are not the most mathematically adept, and they tend to be the ones who respond the best to this kind of a presentation. And having gone through the project, or even portions of the project, it does make learning trig topics from a traditional text a lot easier to get through. Okay, I think I'm done with my presentation. Let me set this aside. Let's see. Here we go. All right, I'm ready to talk about this. If you've got questions that you'd like to ask or comments that you'd like to make, please.
And I'll remind people who joined us late that we're recording this, but if you make any comment that you want not recorded for posterity, we can easily edit it out before this is made publicly available.
Thank you, Dominic.
And everybody else is currently muted, which is fine. But if you're trying to ask a question, unmute first.
That's right.
What do you think is like the minimum amount a person could realistically and usefully use from your project?
Well, I think it's possible to use as little as a single vignette, although I think there are a small number of interdependencies amongst the vignettes. So it may, I know that one or two of the later tasks may actually draw on results of an earlier task. Let's see.
But they might, I mean, could a person just jump to the end though and accept those as, accept the early results as given?
Certainly, yes. So I think ultimately it's possible to use the vignettes independently, with some preparation, of course.
Sure.
Hi, can you hear me?
Yes.
Deepak?
Yes, this is Deepak. I just like to add something to what Dominic was asking. When I implemented this in spring 2017 in my trigonometry classroom, I basically wanted to do the Varahamihira part only, the Panchasiddhantika, the trigonometry in verse. That's what I wanted to do. But I couldn't just jump to that chapter right away because the tasks were connected, that it would ask you. It's kind of like the building up, and I don't know how I say it, but you got to do the previous task up to like a task 10 is kind of mandatory for you to do that, and then you can do the problems in that particular chapter. So I made my student do those tasks, task 1 to 10, and then took them to the task. I think that it started at 25 or something. I can't remember now, but in the task of Varahamihira's sine table, they needed to do that sexagesimal thing. They needed to understand that before they could understand, make sense of anything given in that verse.
Certainly. In fact, I want to give this opportunity to Deepak. Deepak has some knowledge of Sanskrit and of the traditions of reciting verse from Hindu holy texts. And I was very much impressed. In fact, I met Deepak at a talk he gave at the joint meetings in Seattle a few years ago, where he actually recited a few verses from the Vedas, or was it from the Panchasiddhantika?
No, it was a different book, but that was not in Sanskrit. That was in Nepali. But yeah, it was a mathematical verse.
Well, have you attempted to recite the verses that are found in this portion of Varahamihira's text?
I have actually. I sang a couple of these verses to my student. I mean, they were very impressed by the quality. I mean, they produced all those rhyming they could hear. They were really impressed by when I was doing it in my class. They were like, oh wow, anybody could write this sine table in a verse. How could that be even possible? And that a long time ago. And yeah, I mean, that's definitely the something different they have never thought, but they got to see in the classroom. They enjoyed it.
So next time I teach this, can I type you in to sing for my students?
Oh, definitely. I would love to.
That would be awesome.
Yeah.
Actually, Deepak, would it be possible for you to give us a few seconds of chanting?
Yeah, I mean, I don't call it like this is the very authentic way of chanting it, but still, I mean, I think I'll get very close to what people would do at that time. Yeah, I think I would love to sing the sine table you just had.
Yes.
Because the one you showed us in your presentation, there was a verse 6 and verse 7 you had that will give you the table values of sine with 3 minutes and 45 seconds. So it goes 0 to 30 degree and then 30 to 60 degree. That's how it actually separates that. Yeah, that's what it is. The verse 6 and 7, I think you had it in your presentation.
Here it is.
Right. That's the one. So now I'll do the 6, and if you guys like to hear what is that word by word translation is, so that at least you could make sense of what's really going on in that. So the verse 6 goes like this. Se sajaha surati thayo guna sivagriti vescha vinsatihi sahita panchanarakam satardha trisametam khastiriti lipta. So that's all verse 6. Let me do it one more time, and then I can break down a little bit of that, what that really means. Se sajaha surati thayo guna sivagriti visa vinsatihi sahita panchanarakam satardha trisametam khastiriti lipta. So, I mean, this is verse 6, and you are reading that number there. Those numbers are given not as a number, as an object number. I think that is called Bhuta Sankhya in Sanskrit. So it would just translate, they give you not the number, but the word related to that. So what I mean by that is like that 7, the signs and areas are 7. That 7 is indicated as a swara. Swara means the type of sound you would produce in music. There are 7 types of sound you would produce. I think that's my understanding from here. So 7 is attached to that swara thing. Mm-hmm. So it has a different name for 7 in Sanskrit, but here they are giving you, different word. That's the object number is given to you here. And Tithayo is the number of days and I don't know how to say it exactly there, but the month is divided into the 2 parts. Like one is the solar, that's exactly what they are calling here. Like 15 is given as that 15 days there, and Guna, Siva, Griti, Vista, all those are the object number. So all these numbers are here are given as an object number, mm-hmm. And there are sometimes it is given to you as a number like a Panchanarakam, and second line that means 5 times 9 to say that 45. If you see it plus 18, 45. And to say 45, because they needed to fit so many syllabi in that line. Mm-hmm. So they don't call it like 45 with a different word, but they are saying 5 times 9, mm-hmm. So that it would exactly fit into the syllabi. I know it probably doesn't make sense too much without looking at the words there, but that's my thing.
Well, thank you.
You're welcome.
Deepak. That was wonderful.
Yeah, thank you.
I wanted to show, before we left that entirely, here's an image of a Nepali copy of the Pankasiddhantika. So, and then the image behind it here is of a page of Al-Biruni. So I thought I'd have those on my screen to show you if needed. Anyway, I'd like to open the floor again if anyone else wants to ask a question.
I have a question.
Yes, Marty.
So in the works that you're representing, there are figures that are representing triangles or circles engaged with triangles, and then there's tables. Do the original works have any places where they have a visualization of this the comparative lengths without the triangles? In other words, if you look at, say, Napier has 2 lines that one's supposed to represent the sine and the others, and they're side by side, and it's very close to the idea of a function there relating the 2 line segments. So is there anything comparable to that in any of the works that you looked at?
As far as I know, no. At best, you'll have simply geometric diagrams representing the celestial sphere and the
But they're sort of
AutoCaster and things like that. But there won't be anything approximating what you're describing. In fact, in many of the cases, even the diagrams are much later additions.
So the diagrams are representing generic situations or specific situations in a generic context with the circles and for the spheres and things like that.
Or sometimes, as in the diagram I showed from Ptolemy, you'll see multiple situations shown within the same diagram.
Right, but they don't actually separate the lengths distinctly. They'll only make the tables that have the distinct relationships between the corresponding objects.
Correct. Tables are probably as close as you'll get to functions in the ancient world as we can find.
Okay, thank you.
Mm-hmm. Anyone else? Is there anyone in the webinar who, other than Deepak, has implemented this or portions of this project? Well, I invite you to actually go and look at the project yourself. The project has been used not only in courses dedicated to trigonometry or sometimes to pre-calculus. A pre-calculus course will often have a trig component in it, but it can also be used, as many of these projects are, in dedicated history of mathematics courses, especially those that have thematic approaches, where you can investigate a theme across history. Those are the ways in which I've already seen it implemented. If I could return back to Deepak, I know Cynthia, you shared a bit of chat there asking Deepak to make a recording of this. That was one of the first things I asked Deepak to do years ago. So I'm hoping he does figure out the proper way to do this and make a
So, Danny, I will be traveling to Nepal. You probably know that from your colleague that we have a conference in summer, and I'm hoping, still looking for, just to confirm some, if there are any people who does this from the different brands. I mean, obviously, finding a people who does mathematics and this it's a little challenging, but I think there will be someone to at least give a tentative confirmation that this goes the way I'm doing.
Great, thank you, Deepak.
You're welcome.
Well, folks, have I answered your questions or addressed all the things you'd like me to address? If so, I think it makes sense for us to sign off now. Thanks for joining. And if you take a look at the TriumphsNet newsletters that come across your desk from time to time, we have another webinar scheduled in a couple of weeks. I don't remember the exact date, but you'll get notices between now and then. And for now, have a good afternoon, folks, and I'll talk to some of you later.
Yeah, thank you very much, Danny.
Yep, bye-bye.
Bye.